calculating delta H. Now that we know how to draw Lewis dot structures, I thought we'd go back to the rest of the thermodynamics that we had done earlier in the year. But I do want to remind you of how we calculate delta H of a chemical reaction. So the heat associated with a chemical reaction. So we can predict whether it's exothermic or endothermic, if it releases heat or takes in heat, and how much it does. So I thought of a reaction. I thought, hopefully you remember the contact explosive when we let nitrogen tri-iodide dry and we hit it with a ruler and it exploded and formed, it was pretty loud, and formed a purple kind of gas, purple cloud, which is actually the iodine. So let's write that equation and let's remind you of how to calculate delta H using bond energies. So nitrogen tri-iodide, Ni3. And when this decomposes, of course, you're going to get, it'll just break apart into nitrogen and iodine, okay? Got to balance that, put a 2 there. Now there's 6 iodines, so put a 3 there, okay? All right. Now to calculate the delta H, the standard, the change in enthalpy for this reaction, we need to know what bonds we're breaking and what bonds we're forming. So let's look at the Lewis dot structure for Ni3. Nitrogen has 5 valence electrons. Iodine has 7. So you put 1 here, 1, 2, 6, 7. Put 1 here, put 1 here. Okay. Now there's 2 of them, so let's draw 2 of them. Okay. You don't have to always do this, but okay. So you can tell here that the bonds we have to break are these Ni bonds, and there's a certain value. I'll send you the bond energy chart. I think you'll recognize it. And there's a certain amount of kilojoules it takes per mole of those bonds to break it. Okay, so let's see what bonds are formed. So nitrogen has 1, 2, 3, 4, 5. So it forms a bond here. Now, some of you guys have made some mistakes with this. You can't leave these electrons by themselves, so you're going to lasso those, and you're going to lasso those. It's actually a triple bond. So nitrogen has a triple bond. Iodine has 7 valence electrons. That's just a single bond, okay? And why don't we draw all 3? Okay, if you remember correctly, to calculate delta H, it's broken minus made. So we're going to break these bonds and then form these bonds. And if the energy released when the bonds are formed is greater, the delta H will be negative, which means it'll be exothermic. But if it takes more energy to break the bonds, then it'll be endothermic, not exothermic. Okay, so let's see what bonds we're breaking. We're going to break 6 Ni bonds, N single bond I's, minus, okay, we're going to break a triple bond between 2 nitrogen atoms, and we're going to also break, or form, excuse me, we're going to break a triple bond, we're going to also, we're going to form, excuse me, and then we're going to form 3 of these. All right, so I already looked up these numbers earlier. This is 185 minus, and then N triple bond, it's going to be pretty high, 946 plus 3 of these, and I think it's 151. All right, so this turns out to be negative 290 kilojoules, okay? Negative 290 kilojoules. So it's exothermic. Remember, breaking bonds, you have to put energy into it. So you have to put energy into it to break these. When these bonds are formed, energy is released, Energy's released. It's exothermic. Excuse me here. So let me put this here. So we know that. So we know now that for every 2 moles of nitrogen triiodide, we'll get 290 kilojoules of energy. If you look at, let me show you something up here in the corner here. If you look at an energy profile diagram, if these are the reactants, if this is Ni3, okay, it has a certain energy, where are the products going to be? Are they going to be up here or down here? Yeah, they're going to be down here. So these will be N2 plus the 3I2. So this shows that energy is actually released. The energy that the reactants have is greater than the energy that the products have. So this is exothermic. And a lot of times we'll draw this. This right here is referred to as the activation energy. The energy just needed to get this started. For this particular reaction, contact explosive, it has a really low activation energy. But that's an example of an energy profile for an exothermic reaction. All right, there's one more thing I want to do. Let me erase something here for a second, and we'll show you, okay? One more thing that you haven't seen before. This should look pretty familiar too. Okay, so we can quantify this a little bit, and let's say we have 3.4 grams of Ni3, and we want to figure out how much energy is released. All right, so what we can do is this. We can convert this to moles. So for every 1 mole of Ni3, the molar mass of Ni3 is, I'm just looking over here, 394.71. Now we're going to take advantage of this. We know that for every 290 kilojoules of energy, 2 moles of Ni3 must be decomposed. So that 2 comes from there. For every 290 kilojoules, you need 2 of these, 2 moles of this to break apart, 1 mole of this to form, 3 moles of this to form. Now what we can do is also we can convert this to calories. So we remember 1 kilojoule is 1,000 joules. And then maybe you remember 4.184 joules is 1 calorie. And this is then, this answer, I didn't do it, it doesn't really matter. Just use 2 sig figs here. But that would be the amount of energy that's released if 3.4 grams of Ni3 decompose. So if there's 3.4 grams on the ground, we decomposed it, we hit it, it went off, this many calories of energy would be released. Okay, I hope that helps. What we'll do next is show you how to use Hess's law to calculate the delta H of a reaction, okay?